Alright, in this video, we're going to be working through a couple of special systems using substitution. So, here we go. Noah and Zeke are helping to set up the booths at the fair, and they are each paid $7 per hour to carry wood that is needed to build the various booths. Noah arrives at 7 a.m. and begins working immediately. Zeke arrives 90 minutes later and starts working. So I'm going to code my problem right now. Noah arrives at 7 a.m. and Zeke arrives 90 minutes later. And then they both are making $7 an hour. Okay. So I'm going to start with writing my equation. So we have Noah, and his equation is going to be represented with y equals the money he gets, 7 times the number of hours he's working. And then we have Zeke, and Zeke's equation will be y equals 7 times x minus 1.5, because he comes 90 minutes later. Alright, so let's figure out how much Noah gets after 90 minutes of work. So Noah will get 7 times 1.5. Noah would get $10.50 after 90 minutes of work, or 1.5 hours. So let's see how much each of these guys would make at noon. So at noon, that would be 5 hours after Noah arrives. So 5 hours. So I'll plug it into Noah's equation. 7 times 5. $35. And then Zeke would be working 7 times 5 minus an hour and a half. So that would be 7 times 3.5. And that would be y equals 24.50. So by 12 o'clock, this would be 12 o'clock, 12 noon. After 5 hours of work, Noah would get $35. And because Zeke comes an hour and a half later, he's only going to get $24.50. So because they're both earning $7 an hour, Zeke is never going to make as much as Noah because he's always starting later. So if I wanted to represent this as a system, I would write both of these equations. Y equals 7x, and then y equals 7 parentheses x minus 1.5. And then to make it a system, I'll connect it with those brackets, or those braces, actually. Those are called braces. And so this would be my system. This is my system right here. And when I'm solving this, I can see that my rate that they're both making money at is the same. They're both making $7 an hour. And because of that, they're never going to have the same amount of money. And if we were to graph this, these lines would be parallel. And they're parallel because the slopes are both 7. The slopes are equal. And because of that, there's no solution to this system. We have no solution here. But if we used substitution, we can see that. So because both of them are written in this same way, we can just substitute. So I have y equals 7x, and then I have y equals 7 times x minus 1.5. I'm going to substitute this expression here in for y in my first equation. So this is going to go in here. So I have 7 parentheses x minus 1.5 equals 7x, and then I'm just going to solve this equation for x. So I'm going to distribute this, 7x minus 10.5 equals 7x, and I'm at this point here where I see that I have the same quantity of my variable on both sides, but my constant amounts, negative 10 on the left and I have 0 on the right, are not equal. So that would make this my next step, and negative 10.5 does not equal 0, and therefore there's no solution. So if I were to graph it, I would find that these lines would be parallel with no solution because there's no intersection. But by using algebraic steps with substitution, we can see that there's also no solution. All right, we're going to do another example. All right, and here is another problem to practice with substitution, special cases. So here we go. On Monday night, the fair is running a special for the local schools. If tickets are purchased from the school, you can buy student tickets for $4 and adult tickets for $4. You buy 5 tickets and spend $20. Okay? And so we're going to write an equation that connects the number of student tickets and the number of adult tickets. So I'm going to code my problem. Student tickets are $4. Adult tickets are $4. And then we buy a total of 5 tickets for $20. So I'm going to let X represent my student tickets. And I'm going to have Y represent the number of adult tickets. So my equation would be 4x plus 4y equals $20, because $4 for the times the number of student tickets plus $4 times the number of adult tickets will equal $20, the amount I spent. And then my second equation is going to relate the number of tickets purchased, and we bought 5 tickets. So X is the number of student tickets I bought plus Y, which is the number of adult tickets I bought, should equal 5 total tickets. Okay, and so I'm going to rearrange these equations to be in slope-intercept form. So let's move this one here. I have 4x plus 4y equals 20. I'm going to get the x on the other side. So subtract 4x. And I'm left with 4y equals negative 4x plus 20. Divide everything by 4. And I'm left with y equals negative x plus 5 here. And then this equation, I'm going to get it into slope-intercept form. So I'm going to subtract x from both sides, and I have y equals negative x plus 5. And so we can see by looking at these two equations that they are exactly the same. And when we know that there's exactly the same, when we graph them, these are actually going to be the same line on a graph. Same line. Because when I look at my slope is the same in both of them. They're -1. And when I look at my y-intercept is the same, +5. But we can also solve this system algebraically using substitution. So I'm going to take 4x plus 4y equals 20. And my other equation is x plus y equals 5. And when I wrote them in slope-intercept form, I had y equals negative x plus 5. And I had y equals negative x plus 5. We can use substitution here to solve this. So this is the expression for y. So I'm going to take this and put it over here into that equation. So I have negative x plus 5 on the left side equals negative x plus 5 on the right side. And when we look at this, we remember this from our lessons a couple weeks ago. My coefficient of my variable is -1 on the left side, and it's also -1 on the right side. And when I look at my constant amounts, my constants are also exactly the same. And so when that happens, both sides of my equation are the same. We know that there's an infinite amount of solutions.